So we're working with part 2 of the course now, and we're going to start with some linear algebra. Now you might be saying, didn't we already do some linear algebra? Why, yes we did. But now we're going to be looking at linear algebra in a bit different way, and the reason is because whenever you deal with data, whether your data is like a time series, where you have data that just one-dimensional data that changes in time, or whether you have a multi-dimensional vector, and each of these functions could actually vary in time. So you might have x1 of t down to xn of t, and then you would track those in time, right? Some other cases where you might be working with some data, you might be working with image data. And so suppose I've got an image that's like 640 by 480 pixels. And suppose further that this is not just any set of photos, but the set of faces. Okay. And so we know that when you're looking at photos, right, these are actually arrays of pixel elements, right? So in this case, let's see, how many do we have? 640 times 480 is what, 307,200? So we have 307,200 pixel elements in this picture. And so what you can do is you can talk about this being a subspace of R 307,200, right? And so this, we're identifying that the context in which our problem is happening is a vector space with 307,200 dimensions in it. Right, now whether we can do better than that or not, we'll have to do some analysis, but right now, right, we can say that we've placed our problem from this generic kind of, we're dealing with photos, to a very specific vector space. And as soon as you assign your context to a vector space, all of the stuff that we learned in linear algebra comes into play. Okay, so what do I mean by that? So given vector space H, or sorry, just usually V, given vector space V, right, V is typically defined via a basis. We have a basis for V, and what is the basis? A basis, you can probably not read that very well. A basis is a set of vectors that does two things. It's linearly independent, and it's a spanning set. So a basis is a linearly independent spanning set, right? And so as soon as you have that, right, then you know that any vector x in your vector space V or vector subspace H, I think in the notes I just grabbed a subset of the vectors, but any vector x in V can be expressed as a linear combination of the vectors in the basis. Good. So I guess I'll follow kind of the idea from the notes. So suppose I've got let's say that the dimension, suppose the dimension of V is equal to n. What does that mean? Well, the dimension is the number of basis vectors that you need. So the dimension is equal to the number of vectors in the basis. And you might say, hold on, wait a minute. Doesn't that number depend on the basis? And what would you say from your linear algebra? It does not. So if you have a basis, the number of vectors you have in it is always going to be the same number. And so that number is defined to be the dimension of the space. Good. Okay. So now let's let say v1 through vk be a subset of vectors from the basis. Be linearly independent. Oh, be basis vectors. Basis vecs for subspace space H. Therefore, what's the dimension of H? It is K. Good. Dimension of H equals K. Alright. So now, what we're saying here, what we said here, is if I have a basis for the subspace, then if I let X be in that subspace, that means that X can be written as a linear combination of vectors from the subspace. Good. Or from the basis, I should say. Very good. Now, it may be that, you know, as if we're in Rn, right, then v1 through vk are column vectors. We can store the column vectors, basis vectors, as columns in a matrix. So I want you to be really careful with your language when you're talking about these. So the basis vectors are columns, can be stored as columns in a matrix B, for example. Then how can I rewrite this expression? Well, that can be rewritten as v1 as a matrix with these column vectors times c1 through ck. And so what I can do is I'm just relabeling this as B. I'll write it as red B. And then this is actually, well, let's use a different color. This is defined to be the coordinates of X with respect to the basis in B. Let's see. So I'm going to have, I'm using Lay's notation for the coordinate vector. So the coordinates is a square bracket around X, and then we'll just put a subscript B. Now this usually should be a set and not a matrix down here, but we're going to be a little bit sloppy with our notation since I didn't define the set. I actually formalized that a little bit better in the notes, but you see that. Okay, so the idea again is that you can write X as a linear combination of the columns of this matrix B. By the way, what is the size of everything that you're looking at here? B is going to be where we have k vectors in Rn, so therefore B will be n by k, and so the coordinate vector is k by 1, right? It's really important to keep track of your sizes of things. Okay, that's going to be kind of a critical piece. Okay, so now suppose I say, well, what is the coordinate vector? How do I solve for the coordinate vector? Solve for this. Well, I look over here and I see, oh no, B is n by k. That means B is probably not going to be an invertible matrix. Even if n is equal to k, well, if n is equal to k, then it is invertible, but then we'd have to invert the matrix. So the problem is, at this point, we're looking at this and we're saying, okay, I've got to solve this system of equations, but that's going to take a little work. Is there an easier way to do this? And there is. And so that's the next step I wanted to mention. Oh, before I do that, there is a important point I wanted to note, but I'm running out of time. Jeez, that 10 minutes went by fast. Okay, so next time what we're going to talk about is we're going to talk about the coordinate mapping, as a way of getting a low-dimensional representation of the data. Oops, low dimension. And then we're going to be talking about how to find or how to compute coordinates. Okay, see you then.